All right, get started now. Hello, everybody. Welcome to Circuits ENGR 210 review session. What is it, 7 or 8? Wait, this was homework 7. So, yeah, review session 7. Today is October is the 10th month. Yes, I was right. 10/16. I can't write. Fall break is soon. You have your quiz tomorrow, and then you'll be free. So, today we're going to talk more about capacitors and a little bit about inductors. Um, Before we get started, I heard that there have been some questions about how these review sessions are run. I just wanted to make clear that I do not know what is on the quiz. Um, I'm also not like given particular topics to review for the most part. I'm just kind of going off what was on your homeworks and then what has been on quizzes in past years and what some common quiz questions could look like. So what I'm saying is take everything like I'm not necessarily going to know what's on the quiz. I especially since there's a new teacher, the course is not as like predictable as it used to be. So if I get stuff wrong, like there's not really anything I can do about it. But what I have been told is that for the most part, or pretty much always, whatever is on your homework, those are the topics that'll be on your quiz. So yeah. So I'm just going to write that here. I do not know what is on the quiz. The homework topics are on the quiz. So like these kind of sound contradictory, but I do not know. I'll say exactly. So keep that in mind. And yeah, I'm gonna start today by going over the second quiz question from last week because it's pretty important that you know how to do questions like this for capacitors. Um, so basically the idea with the capacitor, right, when you're writing the capacitor equation, is you find the VC of 0 and you find the VC of infinity, and then you basically just make an exponential function that goes from your VC of 0 to your VC of infinity, like with the charging rate of tau equals RC, right? That's basically what you do. And so in order to find these two numbers, though, you have to be able to do what the second quiz question was asking for last week, which is solving the circuit when the capacitor is in steady state. So I'll go over that. Also want to clear up a misconception I saw from some students, which maybe was based on something I said, but it's still important to understand what I was trying to say. Okay. Oh, this is Mhm. Okay, so the first thing I want to make clear is I know last week I think I said something along the lines of it was some circuit with an op amp and there was like a voltage source and then some funky stuff where like this went up and did stuff over here and this went down to another resistor, but both of these went into the op amp. And I was talking about how, okay, this looks weird, but when you're doing a node here and a node here, you know that this point is 9 volts because there's a 9-volt source there. And if there's a source there, then that tells you what the voltage is. I think some people took that to mean like no matter what. The reason this works is because it's 0 volts on the bottom side, right? If it's 0 volts on the bottom side, then the whole point of a voltage source, right, is it's telling you between the two sides of this voltage source, there is a difference of some amount of volts. So if I have 10 volts here and this is a 2 volt voltage source, then what this is saying is it doesn't matter what the current is here. It doesn't matter at all. You're going to have 12 volts here. So what I saw a lot of people did on this quiz this past week is they saw, oh, there's a 10 volt voltage source here, so they just called this point 10 volts because it says 10 volts and there's a plus here. You can't do that. And similarly, people tried to do that by saying, like, this was 2 volts. This does not work because you don't know what this voltage is. You don't know what this voltage is. So you're saying, okay, if you're saying this is 10 volts, then what you're kind of implying is that you think that this is 0 volts, right? Because this voltage source difference, it's saying, okay, between the left and right side, it is going up 10 volts. So if you were to call this point 10 volts, then you're implying that this is 0 volts. Of course, maybe that's what you want to do. I think that's kind of probably not the easiest way to solve the problem, but of course it would work. Um, but anyway, the long and the short of it, right, is that when you are doing node voltage, the first thing you have to do is label some node as 0 volts. So generally, it's easiest to think about it if you just label the bottom 0 volts, but you have to do that with some node. If you don't do that with some node, you're not like your math just doesn't make sense. So keep that in mind. If you were to do that here, then you'd say, okay, now you could say this is negative 2 volts, but you still can't say anything about this node or this node because you don't know either of those voltages. Okay, now that I've gotten that out of the way, I want to actually show how to solve this problem. So this is asking for V1, V2 at steady state. And so at steady state, a capacitor is modeled as a open circuit, right? So what we can do then is basically say, okay, we don't care about this branch and we don't care about this branch, right? If this is an open circuit, then there is no current flowing through it, right? So we can basically pretend it doesn't exist. Same with this branch, even though there's this resistor here, since there's no current flowing through it at steady state, this resistor might as well not exist because V equals IR. If there's no I, then there's no V. So for doing this, I will just cross out this and cross out this. Now remember, what we're trying to find is that V1 and V2. So we can't like completely ignore it per se, but if we look at this, right, V1 is the difference between this point and this point. This point is 0 volts, right? So this is effectively V1 because V1 minus 0 gets you to there. If I just said that there's no current flowing through here because this is an open circuit, then the voltage here is the same as the voltage here, which means that if this is V1, then this is also V1. So we're going to say this point is V1, right? Because that's all connected. And then for V2, we can do the same thing. This is going to be V2. And now we can do our node equations. Oh, and also I'll label a V3 just for fun. You can do this with just two nodes. You could do just this node and this node, but oh, that somehow made a funky dashed line. I think my Apple Pencil might be dying. But it's kind of more straightforward if you do it with three nodes here. So I'll start with V1. So at V1, we're doing our normal node voltage equations. So I'll start with going down. We have V1 minus 0 over 3K. To the right, we have V1 minus V3 over 40K. And to the left there, we have, okay, V1 here, and then here we have V2 minus 10 volts. Because we have V2 here, and it's saying between this side and this side, there is a 10 volt difference. So if we have V2 here, then this has to be V2 minus 10. So plus V1 minus V2 minus 10 over 40K equals 0. If we want to simplify this equation, let's see. Oh, actually, it's like way easier if you do this with mesh current, kind of, but you can do node voltage as well. I'm gonna do it with node voltage because I've already started. But let's see. If we multiply everything by 40, what's 40 over 3? It's like 13. I'll just leave 13.3 V1 plus V1 minus V3 plus V1 minus V2 plus 10 equals 0. If we shuffle things around, and by 3 there, I mean 0.33 repeating. Okay, actually, I don't really need to go through all of this. It's not going to be worth my time. If you guys are curious about this, check the answer key because this is more last week's quiz. But the key point I wanted to get across was that thing about the voltage sources and that these are open circuits, so there's no current, right? I also saw people like doing mesh current, but then they did a mesh for this loop and this loop, even though there's no current here. So you already know that, like, if this was I1, I2, I3, and I4, like they would just find that I1 equals 0 and I3 equals 0. So you don't have to do the loop. You only need these two loops. That was what I was trying to say there. Uh, the the answers posted on Canvas, I think, have like wait, actually, do they post the answers on Canvas? I don't know if that's just me that can see that. Let me check this. Quiz. Oh yeah, they do. Okay. Yeah, the answers posted on Canvas have doing it with both mesh current and node voltage. So look at that. But yeah, I just wanted to show the setup because after that, most people know what to do. And yeah, now we'll just get on to capacitor questions. So capacitor questions, the key equation you need to know is that VC of t equals V of infinity plus VC of 0 minus VC of infinity times e to the negative t over tau volts for t is greater than or equal to 0. Make sure you have this part. It's just like some silly points that will take off if you don't have it, because technically it's wrong if you don't have a unit or a time frame. And tau is RC, where C is the capacitance of the capacitor, and R is basically the RTH from the perspective of the capacitor. You can hear music in the background. That's my roommate. Okay, so what this will look like is, let's say we have our 2 points. What this equation will end up being, right, is like I said earlier, you'll have your VC of 0 and your VC of infinity, and it'll start at VC of 0 and it'll slowly approach this like asymptotically. I would highly recommend whenever you finish doing your capacitor equation, plug in 0 and plug in infinity and make sure that whatever equation you get at the end matches up with whatever you found for these before. Because if you did that wrong, then like you know your equation is wrong. So yeah, be sure to do that. Um, yeah. And then I'll also talk about inductors. So inductors are basically, so if a capacitor, the whole deal with a capacitor is that it stores charge, right? It stores, if you're being a physics major, you say it stores energy in its electric field. The equation is V equals, or no, it's I equals C dV dt. And this implies that voltage cannot change instantly because it has to be differentiable. Um, the other way to look at this is that V equals 1 over C times the integral of the current. Those are just the same equation. And then for a capacitor, we have V equals L di dt. What this is saying is that current cannot change instantly. And that if you were to like flip this around, this one makes less sense. It's kind of less important. But like I equals 1 over L, the integral of the voltage, which is yeah, doesn't make as much sense. But basically the way to think about a capacitor, or the way to think about an inductor is it's basically the same as a capacitor, but everything deals with current instead of voltage. You can think of I think the good metaphor for an inductor is like a flywheel, where if you think of current as like spinning a flywheel faster, then when you let go of the the flywheel, it keeps spinning, right? In the same way, if you get a bunch of current flowing through an inductor and then you stop like putting a voltage on it, it'll still keep pushing that current that way. The way this works in reality is an inductor is like a loop of wire, and when you run, I can't draw a loop. I'm not an artist. So sad. Okay, sure, good enough. Inductor is a loop of wire, and when you run a current through it, what happens is the way the magnetic field lines up, you basically get a big magnetic field that goes through it. And if you remember from physics, a magnetic field induces a current, and a current induces a magnetic field. There is like a bit of power loss. So once it'll get to the steady state, it'll stay in a steady state. But then when you stop like supplying it with current, this magnetic field is basically like self-sustaining the current continuing to move forward. That's not really important for this class, but maybe that intuition would help a little bit somewhere. I don't know. Um, okay, then the other important thing is similar in the way that it's kind of like the dual of a capacitor. At steady state, an inductor is just a wire, right? If you think about it, an inductor is literally a coil of wire. So at some point, it will just act as a coil of wire. Yeah, that's it. And the inductor equation you'll see is very, very similar to the capacitor equation. It's just that instead of having voltages, it is now with currents. And here, the tau, and so this is going to be amps for t is greater than or equal to 0. And here, the tau is uh, L over R. And the way you can kind of remember this is if you were to have an inductor and it has some current flowing through it, the top one is an inductor, the bottom one is a resistor. If you had some current flowing through here, and then all of a sudden you like disconnected it from its power supply, you can think of it like the flywheel will be slowed down more if the resistor is bigger. So that's why the resistor is in the bottom. So a bigger resistor will make this current diminish faster, whereas a bigger inductor will make it last longer. So that's how you get that. And that's how to think about it. And yeah, other than that, you solve them exactly the same way. It's just this is really the only difference. Yeah. Now I will do practice problems with the remaining 45 minutes. Okay, start with a capacitor problem. Let's see. Use a capacitor problem that I like. Okay, this is a pretty basic capacitor problem. I might have done this last week, actually. I don't know. So you'll probably see little switches like this. All it's saying is that at time equals 0, the circuit is moving from being connected to that top part to being connected to that bottom part. And what that is doing here effectively is disconnecting it from the power source. So this is kind of as straightforward of a capacitor question as you could get. And for this, as I said before, we have to find our VC of infinity and our VC of 0. So to start, we'll find our VC of 0. Oh, and these questions will always say like the switch was in position 1 for a long time before going to position 2. All that's saying is that for VC of 0, we treat the capacitor as an open, and then because it's saying at like VC of slightly before 0, it was in this position for a long time, so it was open. And then since the voltage can't change instantaneously at VC of 0, when we're solving for that, we treat it as open. And then for VC of infinity, again, for the same reason, it's open. But let's start by solving for VC of 0. So for that, we're going to have the switch in position 1. So we have this, and we have our capacitor here, open circuit, and we have this. So if we basically, we're trying to find the voltage between here and here, it's the same as the voltage between here and here. We labeled this again. This is 3K. This is just a voltage divider. If you were to pretend this isn't here at all, right? It's just a voltage source, a resistor, and a resistor. So if we're trying to find the voltage across this resistor, it's just a voltage divider. So we can say VC of 0 is equal to that voltage of the 3K there, which in this case is going to be 12 times 3 over 3 plus 6, which is 1/3 of 12, which is 4. Yeah. And then VC of infinity. Now we're going to connect it like this. We have our 6K and we have our 3K. And if there's no voltage source and no current source in the circuit, then what's going to happen is eventually this capacitor will just discharge its power and the resistors will dissipate all the power. And since there's no extra energy being put into the system, eventually you'll have VC of infinity equaling 0. So basically, if there are no sources, I guess if there are no sources and only one capacitor is a key thing. Only one capacitor. Because like as you saw in the homework problem, it's not always the case. Like the homework question 2, where no current flowed. But yeah, if there are no sources and only one capacitor, then you can assume that your VC of infinity is 0. Okay, and then last but not least, we need to find our tau, which is R times C. So our R in this case, I'll add this note here at t goes to infinity. So this is saying what's the rate of the charging or discharging going to be? In this case, it's going to be discharging, but so it's the Thevenin equivalent resistance from the perspective of the capacitor. All that's saying is if we were to send current out this way out of the capacitor, what is the resistance it sees? So it can either go this way or it can go this way to get back to here, right? So these two are in parallel because they're the other way, like this is connected. These two are connected here and they're also connected here. So both sides of both of the resistors are connected, so they're in parallel. Either way, you're going to get that R equals 6 times 3 over 6 plus 3K, which is 18 over 9, which is 2 kilo ohms. And we were given the capacitance, so ultimately tau is going to be 100 micro times 2 kilo. This will be 2,000 milli, which is just 2 seconds. Okay, now plugging this all back into our original equation, where it was VC of t equals VC of infinity plus VC of 0 minus VC of infinity times e to the negative t over tau. What we get here is that we have 0 plus 4 minus 0 e to the negative t over 2, which is just 4 e to the negative t over 2. Volts for time is greater than or equal to 0. And that would be your answer. So yeah, that's how you do it. I'll do like 2 more of these. And this next one I'll do will not have the time at infinity voltage be 0. Yeah, sure, I'll do this one. Okay. If you ever have any questions, feel free to ask them in the chat. I do have that open. Or just ask with your mouth because we are in a Zoom call. Okay. And it is asking, it's defining VC as being positive on the right and negative on the left. So we have to first find VC of 0, and I also have to label all these resistors. Okay, so VC of 0. Okay, at time equals 0, I will copy this. I don't want to draw it again. And time equals 0, this was not there, and this was here. So how do we solve this? Good question. Um, Basically, we look at what we can find first, which in this case would be this part here is basically a voltage source, or you can just, however you want to think about it. If you want to do a source transform, you could. But for me, right, if you have some current going out this way and some current going in this way, like all the current has to go through here. So the voltage difference between here and here is just going to be V equals IR for this current source and this voltage source. So, um, yeah, if you wanted to, okay, I guess if you wanted to do this the most like explicit way, you have to label some node as ground. I'm going to do this one because I want to, because since there's going to be no current flowing this way, right? How does the professor do it in this answer key? Oh, okay. Yeah, actually, it's very straightforward. Okay, yeah, if we label this as ground, keep in mind, even though this is still the bottom side, there's a resistor here, so this is not ground. Okay. Um, but anyway, since this is an open circuit, there's no current flowing here, right? So if this is 0 volts, then actually this is 0 volts. And then if we go up 24 volts here, there's still no current flowing through here, so this is 24 volts. So I'll label that as 24 volts. And then if we want to find the voltage here, it's very simply just going to be V equals IR, which is 4.5 times 4. The kilo and the milli will cancel each other out. So this will end up being 18. So then VC of 0 will be 24 minus 18, which is 6 volts. Okay, now for, wrong tool. For time goes to infinity. Now, instead, we're going to remove this part because it's no longer connected. And this gets connected as such. So now we can look at this circuit the exact same way. So I'm going to label this ground. As time goes to infinity, this will act as an open again. So if this is ground, there's no current flowing this way, then the resistor has no voltage drop. This is ground, this is ground. So this point is going to be 0 volts. And the exact same math we did before finds that this point is 18 volts. Now, VC, because of the way it was labeled in the question initially, with the plus on the right and the minus on the left, we have to keep that the same between the first part and the second part. So VC of infinity would actually be 0 minus 18, so it would be negative 18 volts. Then if we want to find the tau, or the time constant, we have to, again, look at it as a Thevenin equivalent resistance. If you remember, for Thevenin equivalent resistance, we neutralize the sources. So this will become an open circuit because it's the current source. Zero current happens when you have an open circuit, right? So that's why we have it open. So ignore this part. And then what would the Thevenin equivalent be from like this point to this point? Well, you just go through the two resistors. So it would just be 4K plus 1K. So in this case, it will be, oh, and I didn't label this was 100 microfarads again. Um, so it's just going to be 4K plus 1K times 100 microfarads. So it's going to be 5 times 100, 5,000. Kilo times micro gets you milli. So we have 5,000 milli, and that's 5 seconds. So writing it all out down in the final equation, Vc of t is going to be equal to Vc of infinity, which is -18, plus Vc of 0, which is 6, minus Vc of infinity, times e to the -t over tau. And then if we simplify this, we get -18 plus 24 e to the -t over 5 volts for time is greater than or equal to 0. Now that I think about it, you might have had this question on your homework, because I remember seeing this number when I was grading. But either way, it was good to show how to do it. Okay. Let's see if I can find one more capacitor question to do before doing an inductor question. Um, yeah, sure, this one's kind of straightforward. This one I'll show you how fast I could do this and how fast you can do it too. Mhm. So again, it's just asking for Vc of t. Actually, let's pretend this one is asking for Ic of t. If you get a question like this, all you have to remember is that the current is equal to the capacitance times the derivative of the voltage. And do you know how to take, you guys should all know how to take a derivative, I would hope at this point. So if you were asking for the current in this question, I equals C dV dt, this would just be, okay, we take the derivative of the voltage, which is, or first we can multiply by the capacitance, so it's 100 microfarads, times the derivative of this is just going to be -1/5 times 24 e to the -t over 5. And then you'd have that amps, or like these, this would, you'd have farads times, apparently farads times volts will equal amps because that's what the units are telling me here. Actually, it'd be like 1/volts. Or no, it's just volts. Volts per second. I don't know. Ignore the units, honestly. Ignore the units if you're using an equation you know works. Pay attention to the units if you don't know that it works. But in this case, you know this is a real equation. I think this is saying that farads times volts per second would give you amps, because this would be volts and this would be seconds. Yeah. But yeah, ignore that. And this would just be your final answer. Amps for time is greater than or equal to 0. So remember this equation as well. That's all I'm saying. But let's say this is the question it was asking us to do that. This means first we have to find Vc of t. And to do that, we do it the exact same way. And this time, just to kind of talk you through how you could look at this, I'm not even gonna redraw the circuit because this one looks simple enough that you could just do it by looking at it. So for Vc of 0, right, when the switch is in that left position here, what we have is, okay, we have the voltage source here, which I didn't label as 24 volts. And then this is an open circuit, right? And it's connected here and here. This is just a voltage divider. So Vc of 0 is just going to be 24 times 5 over 5 plus 3, which is 5/8 of 24, which is something. I should be able to do that because 24 is divisible by 8. 24 times 5 over 8. This is 3, and this is 1, and then this is 15. That checks out for me. Okay. Oh, yeah, that makes sense. Okay. 15 volts. Then for Vc of infinity, now it's connected this way. And here, since this is an open circuit, right, this resistor at time goes to infinity. This is an open circuit, and this is the only path for current to flow. So this resistor will have no voltage drop. So this will very simply just be the voltage that I also forgot to put here, which is just 30 volts. And then for VC of infinity, we also need to find that Thevenin equivalent resistance for the time constant. And this is the R for, so it's RTH for T is greater than 0 circuit. So we're looking at this half of the circuit, right? And the Thevenin equivalent resistance from the perspective of the capacitor is, okay, it goes through this 4K, and then this is a short when we're doing this, so it's just 4 kilo ohms. So it's going to be 4K times 0.5 millifarads. Milli and kilo cancel, so we just get 2 seconds. Because the time constant does have a unit of seconds. So then if we're writing our final equation here, we'd have it's VC of infinity minus, no, plus VC of 0 minus VC of infinity times e to the negative t over tau, which in this case is 30 plus 15 minus 30 e to the negative t over 2, which is 30 minus 15 e to the negative t over 2 volts for a time is greater than or equal to 0. And as I was saying at the beginning, it's a good idea to check your work and make sure you did this equation right. So if I were to plug in t equals 0, right, then this will be 30 minus 15 e to the 0, which is just 1, right? So this is 30 minus 15, and that's 15, which is equal to our VC of 0. So we know that we did that right. Likewise, if we plug in infinity, we get 30 minus 15e to the negative infinity. E to the negative infinity, if we remember, right? E to the x looks like that. So if we go all the way that way, it's effectively 0. Come on. So this is just 30 minus 0, which is 30, which is the same number we found up there for VC of infinity. So that means we know we did our equation right. Yay. So that would be that. But then it's asking for I. So I equals C dV dt, which is 0.5 millifarads times the derivative of what we just had here. So the derivative is going to be, so plus, and then negative 1/2 by the chain rule times negative 15 e to the negative t over 2. So we have, oh wait, and it's not plus here. Whoopsies, it's times. So now we have 0.5 millifarads, or 0.5 m times, what is this, like positive 7.5, I think. Yeah, e to the negative t over 2. So however you want to write that, it's like, what's half of 7.5? I should know that. 3.75, true. 3.75 e to the negative t over 2, and then you could write it as milliamps because there's an m there for t is greater than or equal to 0. And yeah. Okay. Now I will do inductors. Probably should have done those earlier, but it's fine. Okay, where is an inductor question that I can go through? Okay, here's a pretty straightforward one. So the key thing to remember with inductors is that at steady state, they are like a wire. And other than that, we solve them quite similarly to capacitor circuits. Okay, so we're going to do this the exact same way. We start by looking at the circuit. Oh, and let's say this question is asking for, I'll go all the way and say it's asking for VL of t. And VL of t is going to be V equals L di dt. So that means we have to find IL of t. So we start by looking at before the switch moves. So this is t equals 0 minus, I suppose. And in this case, the switch is in that top position, right? So this is disconnected, and the circuit looks like this. So what will be the current flowing through that inductor at time before the switch closes? Well, if we remember, an inductor at steady state is just a wire, right? So we can think of this as a wire. What is, if we have a path that looks like this in a circuit, we have a wire in parallel with the resistor. The resistor effectively gets shorted, it doesn't matter. And that's exactly what we see here. We have a current source, and then it goes to a split where there's a resistor, and a short circuit. So what's going to happen here is just all the current is going to go through that inductor. So in this case, very easily, just IL of 0 equals 0.4 amps. Okay, next up, when t is greater than 0, it's connected like this. So effectively, this part of the circuit gets cut out. And now, just like I said with the capacitor question earlier, if there are no sources and only like one capacitor and one inductor, then we know that just IL of infinity is going to be 0. Because whatever energy has been stored up in like the magnetic field of this will be dissipated as heat through these resistors, as the current flows through them. Then last but not least, we need to find our tau, which we remember is L over R. And again, just like it was with the capacitors, it's the Thevenin equivalent resistance that the inductor sees. So in this case, it's drawn like as easy as possible. It's just going to be, wait, so R is RTH for t goes to infinity circuit. So in this case, it's just going to be if we started at one end of the inductor and we're looking this way, right? You can go here or you can go here, and these two are in parallel. So just these are in parallel. So R equals 60 times 120 over 60 plus 120, which my gut is telling me is going to be 40, but I will check anyway. 60 times 120 over 60 plus 120. Ooh, okay. 40 ohms. So this is then 0.2 henries over 40 ohms, which is 5 milliseconds, or 0.005. Then if we go to write our current equation, IL of t equals, okay, it's IL of infinity, which is 0, plus IL of 0, which is 0.4, minus IL of infinity, e to the negative t over tau. And then if we rearrange things, we get 0.4 e to the negative and 1 over 0.005 is going to be like 200. So if you have a decimal in the denominator, it can be nice to put it up there. And this would be amps for time is greater than or equal to 0. What this is saying is if we think about graphing this, it'll start as 0.4 and then it'll go down to 0, which makes sense because we said, okay, before the switch moves, we have 0.4 amps flowing through here. So that's why at 0, it's 0.4. And then after the switch moves, it's just going to discharge this over time until it goes down to 0.
Can you quickly re-explain how you got like I of L of 0 to be 0.4?
Hmm. Yeah, so with this circuit, right, the key thing that we want to remember is that an inductor at steady state, so like the same way that a capacitor is an open circuit, I think I wrote this down here. So the same way a capacitor at open circuit or at steady state is like an open circuit, an inductor becomes a closed circuit, like just a wire, right? So if we look at this circuit, right, we have a zero point 0.4 amp current source here, and then we have three things in parallel. We have two resistors and then the inductor. So at time is right before the switch closes, we can assume the switch has been in this position for a long time, so the inductor will be acting as a wire, right? If we were to basically put a wire on both sides of these resistors, then all the current is just going to prefer to go through the wire because there's no resistance. So that means the entire zero point 0.4 amps will just go through the inductor because it's zero resistance, it's the shortest path. If you want to think about it like in terms of things in parallel, like if you have some resistance and it's in parallel with zero, it's going to be R times zero over R plus zero, which would just be zero resistance. So if this is zero resistance, then everything has zero resistance. So everything will decide to flow through the inductor. Basically, if you have a short circuit, all of the current will flow through the short circuit. Like it'll ignore any resistors around it. Yeah.
Okay, that makes sense. Thank you.
Mhm. Okay, then last but not least, if we're trying to find the voltage of that inductor, we just have to do that V equals L di dt. In this case, L is 0.2, and di dt is going to be negative 200. That looks awful. Negative 200 e to the, no, negative 200 times 0.4 e to the negative 200t, which is zero point 0.2 times 200 times zero point 0.4. Gets us negative 16 e to the negative 200t. Volts for time is greater than or equal to zero. It's kind of interesting to think about what it means by the negative 16 here. What that is saying is that, okay, if we define this as positive voltage or positive current, right? We can assume that there's like a higher voltage here than here or something. But we say that this is positive current just from how we got this. So we have positive current flowing here. Then what happens is the voltage here, if the voltage is negative, if we remember from our passive sign convention, negative voltage means that we have current flowing in the direction of the voltage rise. So that means that this is positive and this is negative, which makes sense because it's basically acting as a voltage source or a current source. Because if the current was flowing this way before the switch moved, right, that means the current's going to stay flowing that way, which means that it like effectively has that voltage. Sorry if that doesn't make too much sense, but it's a way to think about it. If you understand that, then cool. It's hard to explain, but that's what the negative means here. The negative tells you whether it's this or it's the current's going the other way. But that's back to the passive sign convention you learned at the beginning of the class when dealing with like power. Okay. Then surely I have one more question I can go over somewhere because we still have 10 minutes left. Um, let's see. It's too easy. So no, like, surely I can find one. Hold up. Notes. Come on. Mhm. The second question on this quiz. Yeah, I'll do this one. Okay, this one's a good example. Let me plug in my iPad. Okay, so in this question, it's asking you to find V0 or V naught of t. In this case, the way that I personally would look at this is before even looking at the rest of the problem, there's an inductor in the question, so this is probably an inductor problem. You're in the inductor part of the class, you're probably solving inductor questions. So how does this relate to the inductor current? Because inductors deal with current. Well, we know that for a resistor, V equals IR, and the I in this case, since it's in series with this inductor, is going to be the same. So we know that this is going to be equal to IL of t times 2 ohms. So we have to find IL of t. So, time to do the same thing over and over again. We have to solve the circuit when the switch is in the first position and then when it's in the second position. So, in the first position here, before the switch has moved, the circuit looks like this. And we want to find the current through that inductor. Well, we can do this in a lot of ways, but I think it would be easiest to just basically when you have something weird like this and you don't know what to do, just solve the circuit in some way. Solve like your node voltage mesh current equations. You could do mesh current here. Actually, it's easiest to do mesh current. I will do mesh current. So if we do mesh current here, this is our I1 and this is our I2. Then we know that IL of 0 is going to be equal to I2 because that's what we've just defined. Yeah. So for I1, we have negative 12 plus 2I1 minus, or no, plus 2I1 minus I2. And then this is again minus 4 equals 0. And then for I2, we have, what is this? Oh, and another thing I should point out here, we're just ignoring the inductor for this because the inductor is a short circuit, right? It's just a wire, so it has no voltage across it. All of these terms are voltages, right? That's a voltage, this is a voltage. And since there's no voltage across that inductor, we are just ignoring it completely while we're doing these equations. So, come on. I2 is going to be, now it is positive 4 plus 2I2 minus I1 plus 2 ohms, or plus 2 ohms times I2 equals 0. If we rearrange these equations, we're going to get 4I1 minus 2I2 equals 16, I believe. Correct me if I do this wrong. I am known to mess up algebra. And then here we'll get 4I2, or no, I'll write it the other way. Negative I1 plus 4I2 equals 4. Um, if we want to solve this, I don't know, like multiply this equation by 2 and then add them together. So we're going to have 8I1 minus 4I2 equals 16. We get 7I1 equals 20. So I1 is 20 over 7. That doesn't feel right, but I'll check to see if it is. Well, I guess we want to find I2 more. So actually, yeah, let me just solve for I2 and see if I get the right thing. Because we don't actually care about I1. So if we wanted to find I2 here, then we would multiply this by, we'd like multiply this by negative 4, or by times 4, right? So that this cancels. So then we'd have negative 4I1 minus, or no, plus 16 I2 equals 16. And then we get 14 I2 equals, wait, no, I'm messing something up. Where am I messing this up? One of my equations is wrong. 2 I1 minus I2 equals 8. 2 I1 minus I1 equals 2. Oh, that's what I missed. See, I told you I'd mess something up. There's a 2 here. That makes way more sense. Okay. So I was like, no way it's supposed to have a 7 in the denominator. Okay, there we go. Okay. Anyway, so we're here. This is actually 8, and this is 8. So then we have 6 equals 24. So I2 equals, wait, no, I'm still messing something up. What am I doing? What's going wrong here? Because I'm supposed to be getting a different number.
I
Why
think
is
the
L?
4 is supposed to be -4.
Yes. Thank you. Yeah. Thank you about that. Thank you for that. So it's 4/3. That's I2 is 4/3 amps. That's the outcome. Thank you so much. Okay. Okay. Then moving on, for time is greater than 0. Algebra is really the hardest part of this class, I must say. Oh wait, no. For time is greater than 0, now the switch has moved, so this part is no longer connected. We can ignore all of this. And now, finding the current here is very straightforward for t goes to infinity, right? Because if this is a short, then it's just going to be V equals IR, I equals V over R, and we just have two resistors in series. So it's going to be 12 over 4, or 12 over 2 plus 2, which is going to be 3 amps. And then if we want to look at the time constant, it's going to be L over R. In this case, what is R? Again, it's that Thevenin equivalent resistance from the perspective of that inductor. If we go out one side, come back in the other, there's only one path. This is a short for Thevenin, so we just have 2 plus 2, it's 4. We know what 2 plus 2 is. So we end up with 2 henries over 2 plus 2 ohms, which is 1/2. Now, if we finally find that IL of t, it's going to be our IL of infinity, which is 3. Um, make sure I'm doing this right. Yeah, yeah. 3 plus 4 over 3 minus 3 e to the negative t over 0.5, which is 3 plus, or 3 minus, that's 9/3 minus 4/3 is 5/3, I suppose. E to the negative 2t, if we just divide that, amps for t is greater than or equal to 0. And then we were trying to find V naught of t, so we just have to multiply this by 2, or 2 ohms technically. And so we've got our final V naught of t equals 6 minus 10/3 e to the negative 2t volts for time is greater than or equal to 0 seconds. So yeah, that's an example of a question where the inductor is not, even though the inductor is a short, it does have current flowing through it. Yeah. Okay, well, I am out of time now, so good luck on your quiz tomorrow, and I will end the recording here. Bye bye.